Okay. Sorry for a bit of a late start, but if all goes well, might be able to compensate for it by ending early. Okay. So I've received the submissions for homework 2 from the majority of you. So I like to wait till a good number of them come in before I grade. So I'll be happy to ruin my weekend by grading that. Still not people have turned in the MATLAB one. So once I get again like a majority of those, then I'll get a ruined fall break for grading that. Maybe we'll see. Okay. I hear a lot of voices down there. Not sure what's going on, but okay. All right. So, okay, let me get to the right. Yes.
Did you stop your recording?
Yes, I did. Yes, if you were watching the screen, then you would have seen that already. So, thank you for starting to pay attention. Sorry, I could not resist. Okay, so I have one more portion of this section, 2.2 on computer arithmetic, to cover many things that can go wrong with floating point arithmetic, and so whatever time we have after that, we can take homework questions. Okay. All right. So I explained last time how real numbers are represented in a floating point number system such as IEEE. There's limited storage space for numbers. So in IEEE, double precision, only 53 significant digits are possible. So that creates conditions for a lot of things to go wrong when actually performing arithmetic. So the first issue, there's one that leads to many others, loss of precision. So a limit. What happened? Okay, I'm gonna start this on a new page. It's the bottom of the page anyway. Okay. All right. So limited storage space for significant digits, and so really these two factors together, wide range of possible exponents. Stop that. Can lead to serious inaccuracy when, and especially when working with numbers of different magnitudes. So I'll give an example of that. Okay. So as an example, so I'm going to make up a floating point number system. With these parameters. So we'll work in decimal. And so we have p equals 10. And then for exponents, so the range of exponents that are possible, plus or minus 20. So L is minus 20 and U is plus 20. And then, so the numbers that I'll work with here. So we'll work with a number that is fairly small. So, or actually no, one is fairly large. Okay, so 2 to the 8th. So 256. So with p equal 10, oh sorry, I want 10 to the 8th. Sorry. Okay, so not 256. Okay, so this is a number that's closer to the upper limit because we can only go as high as 10 to the 10. for the exponent part, we can actually go as high as slightly less than 10 to the 11th, because in decimal, the largest possible mantissa would be 9.99999, so slightly less than 10. And then I'll choose another number that is quite small. So say, well, make these numbers a little more interesting. Like 4 times 10 to the minus 8th, and y is 2 times 10 to the say minus 6. Okay. So as a result of that, we just look at x plus y. And right now, I'm just going to compute the result in exact arithmetic. So we have, okay. All right, so we have 400 million for x plus 0.2 for, so 2 times 10 to the minus 6 for y. So we're going to have 400.00002. Now, if I want to express that in scientific notation, which is most conducive to understanding how a number would be represented in a floating point number system, I need to write that as, so 4 point, and so I'm going to have 8 zeros because of what's to the left of a decimal point, and then 5 more zeros because of what's to the right of a decimal point. So 13. Okay, I'm going to move this to another line here. Okay. All right, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 2 times 10 to the 8th. So if we didn't have any limits on precision, then, so we have sufficiently many digits, then we would be able to represent this exactly in this floating point number system. But the problem is, we're only going to have space for 10 significant digits, starting with this one. So 4, and then only 9 of these 13 zeros can be accommodated. So if I were to look at the floating point representation of x plus y, then, so in other words, I'm taking this number and stuffing it into the constrained floating point number system where this is all I have. This many digits, this many possible exponents. So what would the actual number be once it's put in the floating point number system? Well, the mantissa would be 4, yes. So in other words, the number would just be x. Just because y is so small relative to x that it gets lost. Because the true mantissa has too many digits to represent exactly. So everything after these first 10 digits of a 4 followed by 9 of the zeros, gone. So you might as well not have done the operation. Okay. So, admittedly, an extreme example. So one of the homework problems, actually I want to refresh my memory as to which of the problems from this section I assigned. Okay, I did assign this one, so I'm not going to give it away. I have had that problem in the past where I accidentally give answers to homework problems during class. Okay. So problem 17 in this section takes this further. Suppose you're adding a whole list of numbers, so many of them. How does the order in which the numbers are added influence the result when you have limited precision? So problem 17, exploration 17 in this section requires you to think about that. Okay. Now, it's easiest to see this with addition, of course, also subtraction. Now, so there's also an issue with multiplication and division because just multiplying or dividing mantisses leads to digits that can't be represented. All right. So, as an example, I'll try to concoct one in MATLAB here. Okay. So, consider multiplication with p equals 4. Yes, an extreme example to have only 4 significant digits, but it's just to get the point across. So I need to concoct numbers with only 4 significant digits. And I'll make sure I format long. So MATLAB will show me like 16 digits. So that'll help with the example. So first I'll make up a number of 4 significant digits. So 7662. And then y will be another random number. Different magnitude, but also 4 significant digits. So then what happens if I go ahead and just multiply them? Okay, so what do we have here? These digits here, so 2.969025, that's the mantissa of the result. So, but we only have 4 digits. So really, so float of x times y is going to be 2.969 times 10 to the 4th, because any other digits, again, are lost as a result of the operation. Okay. Division in particular. So now with multiplication, if you have a limited number of digits like this, that kind of really puts an upper bound on how many digits you need to represent your result exactly. And you can tell exactly how much precision is going to be lost. But with division, you can take numbers just like these and divide them, and the result could have conceivably infinitely many digits in the exact result, so you're losing a lot more. Out of curiosity, I just made these numbers up, but if I try x over y, yeah, so we have far more digits, and there will be even more than this that are lost. Okay. So any of the operations, the limited storage space for significant digits leads to a loss of accuracy. Okay. So you can count on maybe, depending on where your input came from, maybe these numbers are exact, but that's about it. As soon as you perform any operation on them, almost always, it involves some error. And some numbers that we can take for granted as being able to represent exactly may be true in decimal, but not in binary. So for example, give me a number so an ordinary decimal cannot be represented exactly using a finite number of digits. Pi. So irrational numbers. What's a rational number that cannot be represented exactly in decimal? Yeah, because it's repeating. Now, with binary, so you can represent with various powers of negative powers of 2 exactly, 1/2, 1/4, 1/8, etc. But a number that we can represent exactly in decimal, 0.1, cannot be represented exactly in binary. It has an infinite expansion in binary. So that's unfortunate. But yeah, what numbers you can represent exactly vary from one base to another. If you had, take 1/3 that was mentioned earlier. If you had a base 3 system, then 1/3 can be represented exactly. But not many people work with base 3. But like I mentioned before, it has happened. Okay. So that's one issue, just loss of precision. Okay. A second issue, so it is something that when we generally take for granted with arithmetic, and we cannot anymore. So addition is no longer associative. So we have normally have, if you take x plus y, and then you add, so you compute that sum first, and then add z to it. That is not the same as x plus y plus z. All right. Commutativity still holds, but not associativity. Because the order in which the operations are performed, each operation is going to introduce some error. Again, consider the case of x, y, and z varying widely in magnitude. I just showed you an example where x plus y in the system turned out to just be x. So what if, for example, okay, like if x is large, y is small, but maybe z is of some intermediate magnitude. Maybe y plus z can be represented more accurately than x plus y. So this is something to think about, that the order in which operations are performed matters because there's error happening at every step of the way, and that error depends on the relative magnitude of the numbers you're operating on. Okay. 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 A big one, overflow and underflow. Well, particularly overflow. So underflow can happen. So as an example, suppose I'm, okay. So I want to take two numbers that can be represented in the system exactly, and then I perform an operation on them, and the result underflow. So I'll make up another system. Well, I'll use the same system as before. So still working in decimal, and let's say 10 digits. But really, in this case, it's the exponents that matter. So precision deals with a number of significant digits. Precision deals with p. Overflow and underflow deal with a range of exponents specified by L and U. So I'm going to let, okay, so x equals, let's see, 10 to the, you don't want to have widely varying magnitudes here. And then y equals, okay. So both of these numbers can be represented exactly in this decimal floating point number system. Problems when we perform operations. So if we look at y over x, so that's going to be 3 times 10 to the minus 6 divided by 4 times 10 to the 8th. So that's going to be 7.5 times, so I have 10 to the minus 6 divided by 10 to the 8th. So that's going to be 10 to the minus 14th. But then I also have 3/4, which is 0.75. But I want to normalize this, so I have 7.5 times 10 to the minus 15th is the exact result. But this goes outside of a range of allowed exponents. Exponents cannot be less than minus 10. So this underflows. So what should our result be? That actually was represented in the system. What should we call this number?
Infinitesimal?
What?
Infinitesimal?
But okay. Well, but so the smallest numbers we can represent are in the order of 10 to the minus 10. But now we have something that's much smaller than that. So, yeah, 0. So we just declare it to be 0. And that's perfectly acceptable solution in this case, because you already have a number that's quite small. By declaring 0, whatever computation you're performing with this number can continue. Although there are certain settings where it might be problematic. What if this is a result of a computation where you're expecting something to be non-zero because then you're going to divide by it, and now you're dividing by 0. So you do have to be worried about it for that reason. But that's something that's application dependent. So sometimes I have situations where I'm dividing by certain numbers, and those numbers can get small. So I just add a little something to it, just so the division isn't thrown off. But again, that depends on what you're doing with the number afterwards. So the remedy for a floating point system, which is trying to be as general as possible, is just to say, okay, it's 0. Okay. Now let's go the other way. X over y. So that's going to be, okay. So here I have 4/3, so 1.33. Repeating, well, I'll use as many digits as I'm allowed. 10 digits times 10 to the 14th. Okay. So this overflows. So in this case, we can't just pick an actual real number and say, okay, we're just going to replace the result with this real number. So we call it infinity, or minus infinity, depending on the sign. So in this case, it'll be positive infinity. And I showed examples of it last time in MATLAB where I deal with a number that's too large. I was testing to see what's the largest number I can represent. Once I went a little bit past that, boom, MATLAB would say it's infinity. Well, really, it's not MATLAB that's doing it. It's IEEE that is saying it's infinity, and inf is just how MATLAB will display that. Okay. All right, so when we're performing these operations, we have to be very careful about whether overflow or underflow might occur. And I'm going to discuss a homework problem, and I believe I assigned it. Let me check. It's number 19. Yes. So consider this expression. Z equals the square root of x squared plus y squared. So what can go wrong here, even if x, y, and z, all three numbers in this expression, can be represented in a floating point system? And how can this expression be rewritten to work around it? So there are certain cases where you have, especially when you have numbers that are close to the limits of what's representable, like a number that's close to the upper limit in magnitude or close to the smallest representable number. So those numbers are okay because they're still within the bounds. But then there are certain operations you perform on them that send them out of bounds. And so the thing is, so this number here, z, in most cases, for whatever, if x and y are representable, most cases z will also be representable. But look at what you're doing here. You're squaring x, you're squaring y, adding them, then taking a square root. That creates opportunities for things to go wrong with intermediate results. But it is possible to algebraically rework this expression so that it's equivalent, that avoids the problem. Now, students have a hard time with this problem, so apologies in advance. Okay, it's really a sorry, not sorry, but I'm just warning you up front that this has caused some trouble. But again, think in terms of numbers that are close to the extremes in terms of being large or small. All right. Okay. Now, this issue is the most pernicious of them all, cancellation. I brought this up on the first day of class, the 1991 Gulf War example, where velocity was estimated to be difference in position divided by difference in time. And what happened was, once these numbers, T1 and T2, became particularly large because tracking of Iraqi Scud missiles had been going on for a very long time, days or weeks or whatever. But the difference between them was small. Results of subtraction can be very inaccurate. So what we have here, and unfortunately it was literally true in that case. Okay. Catastrophic cancellation occurs when x and y are the result of prior computations, and that's important because that means they already have error. And you're performing this, performing a subtraction. So x minus y, where x and y themselves are much greater than. So that's what the double greater than sign means. Much greater than the result of a subtraction. So in other words, you're subtracting two numbers that are very close together. That's what leads to cancellation error. So to give you an example of why this is a problem, so it's going to make up two numbers. Okay. Let's see if I can get this just right in terms of formatting. Okay. So let's suppose, as usual, the decimal system, 10 digits. And we're subtracting, okay. Whoops, didn't mean for that letter to sneak in there. So here's my number, 10 digits. And what I'm going to subtract from it, okay. So I'm taking, so this is my x. Well, I'll put this in front. Okay. So okay, so now I can okay, hold on. I want to have some actual space in here. Not sure why it's not doing it. Okay. Okay, so what we have is 1, 2, 3, 4, 5, 6, 7 digits agree. So we have a difference, and unfortunately it's not cooperating with me in terms of, okay, well, let's do it this way, x minus y. And then I subtract the rest, so I get 5, 2, 2. All right, so that is the result. Using all these digits exactly. So think, okay, so if these are the numbers represented with as many digits that we have, you might think, okay, this number is at least representable in the system, but it's totally beside the point. Because remember, x and y came from previous computations. There were actually other digits beyond this that were lost. But x and y are at least represented with a relative error of like 10 to the minus 10, because that's the machine precision for a system like this. When you have 10 decimal digits, actually not 10 to the minus 10, the relative error in x is less than or equal to, stop that. I really hate when it does this. Less than or equal to 1/2 times 10 to the minus 9. So what's happening here is, and this is actually true not just of x but of y, because whatever result in the prior computations, we have some result and the exact real number. Then we have to truncate it to represent it in the floating point system. So rounding error occurs in x and y, but that rounding error is at most this. So we have 10 digits of precision. But here we only have 3 significant digits. That's all we have. So in other words, 7 digits have been thrown away due to the digits that canceled. So anytime you have digits canceling, this is only true for subtraction, not the other operations. Those can have their own problems, but subtraction is really the class all its own in terms of issues of floating point arithmetic. That whatever digits match up, those are digits of precision lost. So that's what happened in this case. These numbers became far less accurate once T1 and T2 got large, because the difference between them was getting relatively small. That threw off the velocity estimate, which threw off the path of a U.S. Patriot missile, causing it to miss the Scud. So there are a lot of cases where this kind of cancellation can occur. You have to look at in your expressions where subtraction occurs. You have to ask yourself, is there a possibility that the numbers being subtracted might be extremely close to one another and lead to cancellation? And if so, is there something that you can do about it? Okay. All right. So what I'm going to do is, can we rewrite problematic expressions to remove subtractions that can cause catastrophic cancellations? Okay. Now, not every subtraction is bad, because we never be able to get rid of them all. So that's a good thing. It's subtraction of very close numbers. Now, I'll give you an example of where something can go wrong. It's actually set up to a homework problem, so I won't get into the problem very far. Okay, but just to give you some background. Something we take for granted, also, the quadratic formula. Bless you. Bless you. Okay, so here we have our very familiar quadratic formula, and let the polynomial consider the quadratic equation x squared plus 10,000x plus 1 equals 0 with, say, p equals 4. So very limited precision here, but just for sake of the example. So what can happen is, so using the above formula yields these roots in the floating point number system of 4 digits. We get x1 equals 0 and x2 equal to minus 10,000. So let's take these roots and substitute them into a quadratic equation, even just the first one. You set x equals 0 in here, and you get 1 equals 0. So it's way off. And the reason why is in here. This subtraction, well, it's really this subtraction, but what happens is A and C are, so the 4AC is very small compared to B squared. Now, I'm assuming that there's a range of exponents is enough to accommodate taking 10,000 and squaring it. But what happens is we have this number being so large, so the square root of b squared minus 4ac turns out to be simply 10,000. Just because the minus 4ac is so insignificant compared to 10 to the 8th, it's just not even included in the result. So then we have a problem here. We have minus 10,000 plus or minus 10,000. So you can see why one of the roots turns out to be 0. So you actually need, even if I try 7 digits, so I give myself more precision, that's still not enough. It takes 8 digits of precision to get a reasonable result for these roots. So problem 22 in the homework, and let me see, I believe I did assign that one. Yes, picked all the good ones. Wouldn't want to deprive you of fun. Is about algebraically rewriting the quadratic formula to remove a problematic subtraction. And one important point to make: at most one of the roots is a problem. Because in this case, the other root, the minus 10,000, is actually fairly accurate. So you have minus 10,000 plus or minus 10,000. So in this case, the plus sign is the one that leads to an inaccurate root. The minus sign is okay, because that's not a subtraction, that's an addition. Okay. All right. So the reason I'm pointing this out is you need two roots. So if you come up with an alternative to quadratic formula, that is only needed to compute for one root that is not viable with this formula. So in other words, you actually have 2 quadratic formulas. Each one of them is safe for one of the roots. So between the 2 formulas, you have a reasonable way of computing both of them. Okay. Now, I'm going to do another example, or actually a couple other examples, involving cancellation and ways you can get around it. Okay. So consider this expression, 1 minus cosine x for x nearly 0. So you're going to take a small number, plug it into cosine. What is cosine of 0? 1. A lot of students at this level still don't know that, or don't remember that. So I'm glad you guys did. All right. Got to celebrate when we can, right? Okay, so I plug a small number into cosine. I get a number that's approximately 1. So therefore, subtracting that from 1 could give me something that is much smaller than 1. So that's something that can lead to a lot of cancellation error. So what we can do is we can rewrite using a trig identity, a half-angle formula, because we have this half-angle formula, that is sine squared x is equal to 1 minus cosine 2x over 2. So if I so what that means is 1 minus cosine x can be written as 2 sine squared x over 2. So as long as this angle is double of this angle, then that works. So this, we don't have that same kind of problematic subtraction going on here. And so I'm going to actually want to confirm this in MATLAB. Okay. So I can let x be something nice and small, like 10 to the minus 4. So then I'll have 1 minus cosine of x. Okay, and sure enough, that's a pretty dang small number, because it's so it's roughly a half times 10 to the minus 9. So I was just subtracting two numbers that are nowhere near 0, getting a result that is very close to 0. That's exactly the situation where catastrophic cancellation comes about. But if I do this, 2 times sine squared x over 2, whoops, that's totally wrong MATLAB syntax, not sure what I was thinking there. Okay, and notice they don't agree exactly. That's because the first one has cancellation error in it. So the difference is noticeable, at least. So sure enough, this kind of rewriting is necessary to get around that cancellation error. So if you have trigonometric expressions, sometimes trigonometric identities can help you. Okay. All right. Now, do another example involving polynomials. Okay. So by polynomial, I concocted this in advance, but, okay. 1 minus 6, 15 minus 20, 15 minus 6 is 1. Okay, so this polynomial is x squared minus 6x to, x to the 6 minus 6x to the 5th plus 15x to the 4th minus 20x cubed plus 15x squared minus 6x plus 1. Okay, so that's a polynomial that is represented by the vector p. So next what I'm going to do is I'm going to make a vector of x's that are all very close to 1. So 0.995, and we'll have a nice small spacing here. 0.0001, up to 1.005. So I'm going 1 plus or minus 0.005. Okay. And then I want some y values. So y is equal to polyval. So I'm just plugging in these x's into a polynomial y. Okay. Now I'll go ahead and make sure I have no figure windows open, and then I'll plot them. Okay, and thankfully that looked like how I expected. So notice there's a whole lot of oscillation in here. So you think, okay, well maybe that's the way it's supposed to behave, right? Although it seems kind of odd for a polynomial that's only of degree 6. Because a polynomial, you've seen graphs of polynomials all the time. Do they ever look like this? No, they're smooth curves. So certain functions may do this, but a polynomial definitely isn't one of them. That suggests that something is amiss. Now, let's take a look at the roots of this polynomial. Well, they're not really supposed to be that. Did anyone guess from looking at these numbers what the roots are supposed to be?
1.
Yeah, 1 repeated 6 times. So the coefficients that I gave you, these are coefficients of x minus 1 all to the 6th power. I just went ahead and pre-expanded it, and these are the coefficients. So let's graph the same polynomial a different way. So I'll make a new figure window, take the same x values, so plot x, and then I'll have x minus 1 raised to the 6. Okay. And sure enough, look what we have here. We have a smooth curve that we would expect from such a low degree polynomial. So what happened here? Because here we do have subtraction. We have numbers that are very close to 1 being subtracted from 1, and yet this one turned out to be the more accurate graph. So what gives? So the thing is, yes, there is some cancellation error in here. But we're talking like a number such as like 1.005 at the most being subtracted from 1. So a very small number of digits would be lost as a result of the subtraction. But let's take a look at the other option, one that produced a highly oscillatory graph. So I'm going to pick one of the x values. Okay. So that's going to be 0.995. Now, I'm going to raise, so I'm going to show you what happens when I substitute this into a polynomial on a term-by-term basis. Because if I just plug it into polyval, it'll just give me the final result. And that doesn't really tell us anything. So I need to raise this number to all the powers from 0 to 6. So x1 raised to powers is x1 dot exponent. And I need to go in reverse order from 6 all the way down to 0. So that's 6 colon minus 1 colon 0. And that'll give me... Wait. Okay. I'm going to do format short here. Okay. So this is the first x value raised to the 0 power, first power squared, cubed, 4/5, 6. All right. So now what I want to do is I'm going to take all of these powers of x and multiply them by the coefficients. So coefficients are in p. I multiply them by x1 p. So dot multiply because I'm multiplying two row vectors, element by element. And these are the numbers that I get. So in other words, when plugging this x value, 0.995, into the polynomial, these are the individual terms that I now have to add up to get the final result. Now, let's look at the y value. The y value I'm supposed to get, in the order of 10 to the minus 14. We saw that in the graph. So, let's suppose I add up all the positive terms. I'm trying to avoid an unsafe operation for as long as possible. So, I have 7 terms. So terms 1, 3, 5, and 7 are positive. So, the first sum will be... wait, I need to do this again. Okay, so these are the terms that we see here. So the first sum is going to be terms, sum of, well, let's do it this way. No, I won't. Trying to minimize typing. So I take terms 1, 3, 5, and 7 and add them up. So this is the sum of all the positive terms. Then I add up the negative terms. Elements 2, 4, 6. Wow, those numbers look really similar. Let's take a closer look. I'll make them a column vector so we can see them close to each other. Wow, look how close those numbers are. They only differ in the last digit. So in the first case, x minus 1 raised to the 6th power, yeah, I gave away maybe 3 or 4 digits of precision. Here I practically gave them all away. So that is extremely bad cancellation error. So that's why there are cases where, yes, there's some subtraction, but that expression could be written in such a way as to make the subtraction better or worse. So, and the key here is, like I said, cancellation error occurs when the two numbers you're subtracting, your x and y, are much greater in magnitude than the result, x minus y. So how bad it is depends on how much greater they are in magnitude than the result. Because these numbers, very decent size, it's just that they're so much larger than their difference. Here I go. I add the two together and get something like that. I mean, there's pretty much no precision whatsoever in that result. It's pretty awful. Okay. By the way, I realized last class I had done some things in MATLAB. I forgot to post that. I do have it saved, so I promise I will get that posted, and along with this right here. Okay. So any questions about cancellation error? So yes, there's a couple problems, one involving quadratic formula, but then there's another one with a different expression where the job is to algebraically revamp them to avoid the problematic subtraction. And the thing is, often it's just for certain numbers. Like you can have a function that can be evaluated just fine for most x, but maybe x near a certain point. Like this function here, if I plug in other x values that are away from 1, there's no problem. I'll pick a different vector of x values. So I'll go back to figure 1. That's so awful right now. And I'm going to pick different x values. Well, I'll just take x. X is clustered near 1. So I'm just going to add 1 to it. So now these values are clustered near 2. I will plug it into the polynomial and plot them. Look, no problem. So, because in that case, there wasn't a pernicious cancellation error to deal with. If I had gone through the same thing of coming up with numbers here, we would not have this situation. So in this case, it's only near x equals 1 that evaluation of a polynomial in that form is an issue, because that's where all the roots are. Okay. Does anyone have any homework questions? Has anyone started on homework 2.2? Yeah, I didn't think so. I mean, it is a whopping eternity of 5 days away. So, okay. Yeah. Well, really, that was my plan from the start of the semester when I was scheduling everything. I thought, okay, if I have an assignment where I covered a section finished covering a section on Thursday, and then make the assignment due Tuesday, that works with how students are because they'll wait until Monday night, or maybe even Tuesday morning to get started on it. Therefore, enough time. So, okay, because it's only 7:30. You sure you don't want to stick around? So I have nothing left to cover in this section. So, we actually start getting away from the computer sciencey stuff now and going into polynomial interpolation. So, and there'll still be MATLAB to do. You have that all semester long. Sorry. Again, not sorry. Okay. Well, those of you who were in that taking a test last period were probably have your brains totally fried anyway. So, all right. I guess we're calling it good. This won't happen every time. Sorry. I am sorry in that case.
You can just make it happen on
I'll keep that in mind.
Nice stuff.